when multiple AC sources are connected in parallel. As is the case in most distributed power networks, or microgrids, the power contribution of each generator to the network may be controlled using the frequency setpoint and voltage setpoint when operating in Droop mode. Active power measured in watts is affected by the phase angle difference between generators and adjusted using the frequency setpoint. Reactive power measured in reactive volt amperes is affected by the voltage magnitude difference between generators and adjusted using the voltage setpoint. Droop mode is the commonly adopted mode used to allow predictable and controlled load sharing between AC sources. The voltage and frequency of each generator is allowed to move around by a defined amount as a response to load conditions. The Droop equation is shown, which is considered for generator frequency response to a real power load. The same method can be applied to voltage response to a reactive power load. We shall consider a 50 kilowatt load being applied to the generator. The frequency Droop constant, which is user configurable, is set at 2% for this example. The voltage and frequency set point is assumed to be 400 volts and 50 Hz for this example. The rated current of the generator or inverter is 200 amps. From these values, the rated power is able to be calculated as 138 kilowatts. When the rated power is worked out, the load regulation characteristic, which controls the Droop response, is able to be calculated. This load regulation characteristic is measured in watts per hertz and hence demonstrates the effect of real power on generator frequency. In the example, the inverter will droop its output frequency by -0.361 Hz from 50 Hz nominal with a 50 kilowatt load in order to operate and load share with parallel sources. Looking at the generator Droop response in a different light, when the generator is connected to a stiff grid, or a parallel isochronous source, or an effectively infinitely backed grid, like a national grid, the power transfer from the generator to the grid can be controlled by adjusting the frequency setpoint. In the previous example, we saw that when a 50 kilowatt load was connected to a generator, the Droop response reduced the generator output frequency by -0.361 Hz from 50 Hz nominal. If the grid is stiff at 50 Hz, and the generator needs to contribute 50 kilowatts to the grid, then the generator frequency setpoint shall be increased to +0.361 Hz from the bus frequency, which is 50 Hz. It is important to note, if the generator operates alone with no parallel sources, the load will dictate the power contribution of the generator to the bus.